Welcome to Akool Research Publications. Today, I'm going to present a paper, which is about generative salient object detection using a latent space energy-based model. Salient object detection aims at highlighting salient object regions in images, which is binary image segmentation. For example, given an RGB, or RGBD image, the salient object detection algorithm outputs a binary saliency map to indicate the salient object. Such a task has a wide range of computer vision applications, such as image understanding, image captioning, object detection, unsupervised video object segmentation, semantic segmentation, and so on. A conventional framework for deep salient object detection involves two main modules: a convolutional encoder-decoder for saliency map generation, and a loss function to guide the encoder-decoder for parameter updating. The goal of the above two modules is to achieve a mapping function from the input image space to the output saliency space. Two main issues exist in the conventional deep saliency frameworks. First, the sliding window-based convolution operation makes the deep saliency model less effective in modeling the global contrast, which is essential for salient object detection. Second, the one-to-one deterministic mapping mechanism makes the current framework impossible to estimate the pixel-wise confidence of model prediction. Also, deterministic methods usually do not have stochastic property. It is hard to learn from incomplete data. To solve the first issue, this work uses a vision transformer to replace the encoder-decoder. Transformer has achieved great success in natural language processing. Transformer has obtained great interest in the computer vision community to adapt these models for vision tasks, such as classification, object detection, and image segmentation. For example, SWIN presents a hierarchical transformer with a shifted windowing scheme to achieve efficient transformer network with high-resolution images as input. To solve the second problem, we try to study generative modeling of the supervised saliency prediction problem by using a generative model framework. That is, we try to learn the probability distribution of saliency given the image. As we know, VAE and GAN are two popular methods for generative modeling. Some method has already used VAE to model saliency prediction. However, the prior model of the generator in GAN and VAE is assumed Gaussian, which is a non-informative prior distribution that will limit the capacity of the model. Therefore, this work decides to parameterize the prior model by an energy-based model. And the paper learns the prior model from data. Combine these two together, the paper proposes a generative vision transformer with an energy-based prior model for saliency prediction. The model is a latent variable model with Z representing low-dimension latent variables. We use I to denote an image, and S for saliency map. For a deterministic mapping, we just need to learn a mapping from I to S. However, for a stochastics mapping, we need to model the probability of S given I. Therefore, we need to add a random noise, which are latent variables that follow a prior distribution. This will change the one-to-one mapping into a one-to-many mapping. For the energy-based prior model, we parameterize the energy function by a trainable deepnet. We jointly train the parameters of the energy-based prior and the transformer network by maximum likelihood estimation. The key is to compute the gradient of the log likelihood with respect to the parameters, which can be decomposed into two intractable expectation terms. To estimate the learning gradients, we adopt Markov chain Monte Carlo sampling to evaluate the intractable prior and posterior distributions of the latent variables, and use the sample average to approximate the expectation. The learning algorithm alternates the sampling step and the model update step until the algorithm converges. We present a detailed description of the learning algorithm and the prediction algorithm of the proposed framework. Once the model is trained, we can perform salient object detection by sampling from the learned conditional distribution. To be specific, given an input image, we first sample a noise vector from the energy-based prior distribution, and then use the transformer network to map the image and the noise vector into the saliency map. The results show that our model can generate diverse predicted saliency map for an image. We further propose an adversarial learning algorithm and a variational inference algorithm as alternatives to train the proposed generative salient object prediction framework. Our framework using energy-based prior can be easily generalized into both adversarial learning and variational inference frameworks. We apply the proposed frameworks to RGB salient object detection tasks. Experimental results show that our generative saliency model with an energy-based prior can achieve not only accurate saliency predictions but also reliable uncertainty maps that are consistent with human perception. We also apply our model to RGB salient object detection tasks. Here are some qualitative results. Let us briefly summarize the proposed model in this paper. From the machine learning perspective, our model is a top-down deep conditional generative model using EBM as a prior. The MLE learning algorithm derived from the proposed model is based on MCMC inference for the posterior and MCMC sampling for the prior, which makes our framework more natural, principled, and statistically rigorous than others. On the other hand, the traditional adversarial learning and variational learning techniques can be easily adapted to the proposed EBM prior-based generative model, which can bring in benefits of good performance and fast inference respectively. From the computer vision perspective, our model with a special network designed to handle saliency prediction is a new member of the family of saliency prediction methods. In comparison with the traditional discriminative saliency prediction methods, our generative method is natural because it models the saliency prediction as a conditional probability distribution. Further, the EBM prior leads to more reliable uncertainty modeling compared with the conventional generative models. For more information, please refer to the following paper. Thanks for your listening. Bye.